matter. We have gas, liquid, and solid. Gas. Total disorder, much empty space. Particles have complete freedom of motion. Particles apart. Why the particles apart in gas? Because in gas, particles are in continual straight line motion. The kinetic energy of the molecule is greater than the attractive forces between them. Liquid. Cluster particles are free to move relative to each other. Particles close together. Why particles close together in liquid? The attractive forces in a liquid are strong enough to keep the particles close together, but weak enough to let them move around each other. Solid. Particles are essentially in fixed positions. Particles close together. Why the particles of solid are fixed together? The attractive forces keep the particles together tightly enough so that the particles do not move. The attractive forces between particles are strong enough to hold a specific volume, but not strong enough to keep the molecules sliding over each other. Because in the solid and liquid states particles are close together, we refer to them as condensed phases. These phases of matter are said to be condensed phases because the intermolecular phases are fairly strong as compared to those in gases. The state a substance is in at a particular temperature and pressure depends on two antagonistic entities: the kinetic energy of the particles, the strength of the attractions.
The intermolecular forces. The attractions between molecules are not nearly as strong as the intramolecular attractions that hold compounds together. They are, however, strong enough to control physical properties such as boiling and melting points, vapor pressures, and viscosities. The intermolecular forces are the forces of attraction or repulsion which act between neighboring particles, for example is the atoms, molecules, or the ions. These intermolecular forces as a group are referred to as van der Waals forces. The first type of intermolecular force we will consider are called van der Waals forces after Dutch chemist Johannes van der Waals 1837 to 1923. Van der Waals forces are the weakest intermolecular force and consist of dipole-to-dipole forces and dispersion forces. Van der Waals bands are mainly of three types such as hydrogen bonding, dipole-to-dipole interactions, and London dispersion forces. Hydrogen bonds occur in inorganic molecules such as water and organic molecules such as DNA and proteins. Dipole-to-dipole forces are attractive forces between the positive end of one polar molecule and the negative end of another polar molecule. And lastly, the London dispersion forces is the weakest intermolecular force. It is sometimes called an induced dipole to induced dipole attraction. So next is the ion-to-dipole interactions. A fourth type of force, ion-to-dipole interactions are an important force in solutions of ions. The strength of these forces are what make it possible for ionic substances to dissolve in polar solvents. Ion-to-dipole interaction occurs when an ion encounters a polar molecule. In this case, the charge of the ion determines which part of the molecule attracts and which repels. A cation or positive ion would be attracted to the negative part of a molecule and repelled by the positive part. An anion or negative ion would be attracted to the positive part of a molecule and repelled by the negative part. Dipole-to-dipole interactions. Molecules that have permanent dipoles are attracted to each other. The positive end of one is attracted to the negative end of the other and vice versa. These forces are only important when the molecules are close to each other. Solid red lines is the interaction between any two opposite charges is attractive, while the dashed blue lines, the interaction between any two like charges is repulsive. Dipole-to-dipole interactions are a type of intermolecular attraction, the attractions between two molecules. The positively charged portion of one molecule is attracted to negatively charged portion of one another molecule. Since many molecules are polar, this is a common intermolecular force. The dipole-to-dipole interactions. So now, we are going to determine the molecular weight, the dipole moment or the value of Debye, and the boiling point of the substance. Thus, the first material is profane, which has a molecular weight of 44, a dipole moment of 0.1, and a boiling point of 321. To determine the boiling point of propane, we must first determine its temperature in degrees Celsius and convert it into Kelvin. The next substance is the dimethyl ether. The process is just like in the first substance. The molecular weight is 46, the dipole moment is 1.3, and the boiling point is 248. Following that is the methyl chloride, which has molecular weight of 50, a dipole moment of 1.9, and the boiling point of 249. Next is the acetaldehyde, which has a molecular weight of 44, dipole moment of 2.7, and the boiling point of 294. And lastly, the acetonitrile, the molecular weight is 41, the dipole moment is 3.9, and the boiling point is 355. The more polar the molecule, the higher is its boiling point.
London dispersion forces. While the electron on the 1s orbital of helium would repel each other and therefore tend to stay away from each other, it does happen that they occasionally wind up on the same side of the atom. At that instant, then, the helium atom is polar, with an excess amount of electron on the left side and shortage amount on the right side. Another helium nearby then would have a dipole in the zenith, as the electron on the left side of the helium atom 2 repel the electrons on the cloud of the helium atom 1. London dispersion forces or dispersion forces are attractions between an instantaneous dipole and an induced dipole. These forces are present in all molecules, whether they are polar or nonpolar. The tendency of an electron cloud to distort in this way is called polarizability.
How to determine whether the molecule is polar or non-polar. If one end of the molecule has a positive charge while the other end has a negative charge, and if the bonds are asymmetrical, the molecule is polar. And if a charge is evenly distributed around a central atom, and if the bonds are symmetrical, the molecule is non-polar. Here are some examples of polar and non-polar molecules. Polarizability allows us to better understand the interaction between nonpolar atoms and molecules and other electrically charged species such as ion or polar molecules with dipole moments. Here are some examples of polar molecules. First, H2O or water. The bonds between hydrogen and oxygen are distributed so that the hydrogen atoms are both on one side of the oxygen atom rather than evenly spaced. The oxygen side of the molecule has a slight negative charge, while the side with the hydrogen atoms has a slight positive charge.
And here are some examples of non-polar molecules. First, carbon dioxide or CO2. It is non-polar molecule because it contains two polar bonds that are arranged symmetrically, but the geometry of CO2 is linear, so that the two bond dipole moments cancel and there is no net molecular dipole moment. Second is methane or CH4. It is non-polar molecule because it does not have the charges present at the end because of finely distributed electrons. And this distribution, which is symmetrical, cancel out each other. And the third one is benzene or C6H6. It only contains C-H and C-C bonds. Since carbon is slightly more electronegative than H, a C-H bond is very slightly polar and has a very small dipole moment. Overall, it has no dipole moment. Hence, benzene is non-polar.
Factors affecting London forces. The shape of the molecule affects the strength of dispersion forces. Long, skinny molecules like N-pentane tend to have stronger dispersion forces than short, and fat ones like neopentane. This is due to the increased surface area in N-pentane.
Factors that affect London forces are molecular size and molecular shape. In molecular size, London dispersion forces are tend to be stronger between molecules that are easily polarized and weaker between molecules that are not easily polarized. And in molecular shape, we have neopentane, which is the gas, and N-pentane, which is the liquid.
This is an example of factors that affects the London forces. Given, chlorine and bromine have approximately the same shape and neither is polar. Upon cooling, both chlorine and bromine form solids. Why? Because London dispersion forces are responsible for the formation of solids. As the elements are cooled, the kinetic energy of the chlorine and bromine molecules decreases, and the London forces are strong enough to overcome the kinetic energy and hold the molecules in a solid. B. At 25 degrees Celsius, chlorine is a gas whereas bromine is a liquid. Why? Because London dispersion forces between the larger bromine molecules are sufficient to cause them to form a liquid at 25 degrees Celsius, whereas London dispersion forces between the smaller chlorine molecules are not.
The strength dispersion forces tend to increase in increased molecular weight. Larger atoms have larger electron clouds which are easier to polarize.
Example of London dispersion forces. Given C2H4, CH4, C3H8, C4H10, C2H6. And this is the arranged molar mass and surface area. CH4, C2H4, C2H6, C3H8, and C4H10. So the largest intermolecular dispersion forces is the butane or C4H10. Why? Because butane has two constitutional isomers called butane and isobutane. Butane is a straight chain hydrocarbon while isobutane is a branched chain hydrocarbon. This is important to note because it offers an example on how surface area affects the strength of the LDFs or the London dispersion forces because the branched chain isomer has a smaller surface area. You could predict a lower boiling point when compared with straight chain butane. And isobutane has a boiling point of negative 13 degrees Celsius while butane has a boiling point of negative 1 degree Celsius. And since it has a higher boiling point, butane has a stronger London dispersion forces.
Which have a greater effect? Dipole-to-dipole interaction or dispersion forces. If two molecules are of comparable size and shape, dipole-to-dipole interactions will likely be the dominating force. If one molecule is much larger than another, dispersion forces will likely determine its physical properties. The nonpolar series SNH4 or thin hydride 2CH4 or methane follow the expected trend. The polar series follows the trend from hydrogen telluride through hydrogen sulfide, but water is quite an anomaly. Hydrogen bonding. The dipole-to-dipole interaction experienced when hydrogen is bonded to nitrogen, oxygen, or phenylene are unusually strong. We call this interaction hydrogen bonds. Hydrogen bonding is a special type of dipole-to-dipole attraction between molecules, not a covalent bond to a hydrogen atom. It results from the attraction force between a hydrogen atom covalently bonded to a very electronegative atom, such as a nitrogen, oxygen, or phenylene atom, and another very electronegative atom. Hydrogen bonding arises in a part from the high electronegativity of nitrogen, oxygen, and fluorine. Also, when hydrogen is bonded to one of those very electronegative elements, the hydrogen nucleus is exposed.
Examples of intermolecular forces present in some molecules.
H2S or hydrogen sulfide. London dispersion force. By default, every compound will have this force of attraction with every molecules and dipole-dipole attraction.
Methanol or CH3OH. London dispersion force, dipole-dipole attraction, and hydrogen bonding.
C2H6 or ethane. London dispersion forces. It is a non-polar covalent compound and no other intermolecular attractions.
Practice exercise. Letter A. Identify the intermolecular forces present in the following substances. And letter B. Select the substance with the highest boiling point. CH3CH3 or ethane, CH3OH or methanol, and CH3CH2OH or ethanol.
Intermolecular forces affect many physical properties. The strength of the attraction between particles can greatly affect the properties of a substance or solution. Intermolecular forces are the forces that bind two molecules together. Physical properties are affected by the strength of intermolecular forces. Melting, boiling, and freezing points increase as intermolecular forces increase. Vapor pressure decreases as intermolecular forces increase. Viscosity. Resistance of liquid to flow is called viscosity. It is related to the ease with which molecules can move past each other. Viscosity increases with stronger intermolecular forces and decreases with higher temperature. Surface tension results from the net inward force experienced by the molecules on the surface of a liquid. Surface tension property of a liquid surface displayed by its acting as if it were a stretched elastic membrane. This phenomenon can be observed in the nearly spherical shape of small drops of liquids and of soap bubbles. Because of the property, certain insects can stand on the surface of water.
Phase changes. When temperature changes, matter can undergo a phase change, shifting from one form to another. Examples of phase changes are melting, changing from a solid to a liquid, freezing, changing from a liquid to solid, evaporation, changing from a liquid to gas, condensation, changing from a gas to liquid, and sublimation, changing from solid to gas. Energy changes associated with changes of state. Heat of fusion. Energy required to change a solid at its melting point to liquid. For example, water has a heat of fusion of 80 calories per gram. It means that it takes 80 calories of energy to melt 1 gram of ice at the temperature of 0 degrees Celsius into the water at 0 degrees Celsius. Heat of vaporization. Energy required to change a liquid at its boiling point to a gas. For example, when a pot of water is kept boiling, the temperature remains at 100 degrees Celsius or 212 Fahrenheit until the last drops evaporates because all the heat being added to the liquid is absorbed as a latent heat of vaporization and carried away by the escaping vapor molecules.
What is the enthalpy change during the process in which 100 grams of water at 50 degrees Celsius is cooled to ice at negative 30 degrees Celsius? The specific heat of ice, water, and steam are 2.09 joule per gram per Kelvin, 4.18 joule per gram per Kelvin, and 1.84 joule per gram per Kelvin respectively. For water, delta H fusion is equals to 6.01 kJ per mole and delta H vaporization is equals to 40.67 kJ per mole. In the givens above, we will use the formula Q is equals to M times C times delta T, which is mass times specific heat capacity times the change in temperature. Solution. Q1 is equals to 100 grams times the specific heat capacity of water, which is 4.18 joule per gram per Celsius, times 0 minus 50 degrees Celsius, which gives us negative 20,900 joule, and we will divide it to 1,000 to make it negative 20.9 kilojoule. Q2 is equals to 100 grams of water divided by 1 times 1 mole of water divided by 18 grams of water times 6.01 kilojoule per mole divided by 1 mole is equals to 33.4 kilojoule. Next is the Q3. 100 grams times the specific heat capacity of ice, which is 2.09 joule per gram per Celsius, times negative 30 degrees Celsius minus 0 is equals to negative 6,270 divided by 1,000 to make it negative 6.27 kilojoule. And lastly, we will add the Q1, the Q2, and the Q3, which is negative 20.09 kilojoule plus negative 33.4 kilojoule plus negative 6.27 kilojoule, which gives us negative 60.57 kilojoule or negative 60.6 kilojoule.
Hydrogen sulfide or H2S, and this is the intermolecular forces. It exhibits dipole-dipole intermolecular forces. Okay. And next is the methanol or CH3OH. It has the hydrogen bonding, dipole-dipole attraction, and London dispersion forces. And next is the ethane or C2H6. It is a non-polar, which means they have no dipoles. Since hydrogen bonds are a special subset of dipole-dipole interactions, this molecule has neither dipole-dipole forces nor hydrogen bonds. Rather, it has only the intermolecular forces common to all molecules, which is the London dispersion forces.